there.
Welcome to this PhD seminar. Today's speaker is Giorgio. Giorgio works on augmented reality and on interaction in augmented reality.
Thank you. Good afternoon. The title of my thesis proposal is Achieving an Effective Interaction in Augmented Reality Environments. The presentation will be structured like this, so we will first see a brief overview of the problem, then we will explore a little bit of state of the art, and then I will show you my first year preliminary results, and then we will go to the future works and what I plan to do to the following 2 years. So the main two problems behind developing an interface in augmented reality is how to achieve a stable augmentation, so how to technically obtain some virtual images which are not jittering, which are not moving around, which are ecologically stable, and so on, and how to achieve an efficient interaction. So like any other interface, we have to validate all the aspects behind the usability aspects. So if any interface developed in augmented reality can be effective to use. So if it is better than traditional interfaces, so for example with WIMP paradigmas and so on. In the state of the art, I split the state of the art in 5 subsections. So we will first see the environmental registration. Then we will go in the differences between different types of head-mounted displays. And then to go to the hand tracking problematic and the introduction of haptic feedback. And finally, the usability design problems, which are related with the human factors. Environmental registration is needed by the augmented reality systems to know where to place the virtual objects, basically. So we need to find an external reference frame to know where to render and how to render the objects in the space. There are 2 main ways to perform some kind of environmental registration. The first one is to use fiducial markers, and the second one is by using SLAM. Fiducial markers are easy to implement because they are easy to track and they are computationally efficient. But the problem of using fiducial markers is that you are not actually registering the environment, but you are only tracking that single image. And the whole reference frame of the virtual world is overlaid on top of the reference frame which is located on the fiducial marker. So for example, if there is a real object which comes in between virtual objects and your point of view, since the real object is not actually being registered, there will be some perceptual paradox because you will still see the overlay, the virtual augmentation, but on top of an object which is on a different depth, which is not coherent with the real depth. On the other hand, if we implement SLAM techniques, we can then interact with real objects, but there are still some problematics related with implementing SLAM because the data representation, for example, of SLAM techniques is often in the form of point clouds. So, for example, there is still the possibility of missing data in your representation. For example, here you can see that there are many black parts in that image because that representation is very sparse. So, of course, you cannot, for example, have a collision with points which have not been registered. There are a lot of SLAM implementation because it is tied with robotics research and self-driving vehicles research. But the different implementation depends on which hardware are you using. So there are implementation from ocular cameras, implementation from stereo cameras, depth sensors, sonars, and so on. Types of devices. There are 2 kinds of head-mounted displays, mainly in augmented reality. The first one is optical see-through devices, and the second is virtual see-through devices. The first one shows the virtual images by projecting the image on top of those slanted glasses by means of mirrors or prisms, which project the image from a small inner projector. Video see-through devices, on the other hand, have a front camera, which can be seen here, which capture a video feed, which is then displayed with the virtual augmentation inside two or one display in close contact with the eyes. Those two kind of head-mounted displays are different in the way they handle the optics of the real-world images. So, for example, here the optics is there are less distortions, because both there is the lack of the parallax between the eyes and the real world, while here there is the parallax caused by the fact that there is a camera which is then generating two views. In the case this headset seems to be monocular vision. And also, for example, if these head-mounted displays shut down, then you can still see through the glass. In that other case, if the powers finishes, you are blinded, and you have if you are working, for example, if you are a surgeon and you are working on a patient with this thing on, it can be not optimal in certain cases. But those are the first implementation of head-mounted displays. Regarding hand tracking, registering the hand is related with environmental registration in some ways, because we both need to register an inner representation of the hand for interacting with the objects, and also to handle the occlusions between our hands and the virtual imagery. There are two main approaches to hand detection and tracking. So the first approach is to perform a full pose estimation of the hand, while the second approach is to perform a simple gesture detection. Performing full pose estimation is a little bit trickier because there are many problems related with hand tracking, because the hand are kinematically complex mechanisms. So they have 26 degrees of freedom, which means that there are a lot of parameters to be found in real time. Since the hand generates a lot of self-occlusions, we have to pair with partial data when analyzing we don't have always that kind of situation where we can see the full hand, and we have to pair with that when designing the estimator. And also the hands move very fast, so they can achieve a speed of 5 meters per second and translational speed, and 300 degrees per second for wrist rotation. So the frame rate of the camera is often slower than the speed that we can move our hands. On the other hand, the gesture detection is faster. There are several different approaches that can be implemented to obtain these kind of results. For example, by skin segmentation, color approaches, or depth-based approaches, and usually they are very fast to compute. However, since you are only recognizing, for example, in this case, this gesture is used for moving the mouse, for example. This is used for the left click, and this is used for the right click. But that means that basically you are using the same interface paradigm of desktop computer, but in augmented reality. You cannot interact in a three-dimensional manner with the holograms, which is limiting in the interaction aspect. Finally, we have the haptic feedback, which is related to the necessity to have an haptic feedback when we touch the objects. Because, however, of course, the virtual objects are not material, so we cannot feel when we touch the objects. There are different. There have been a lot of multiple design over the years, especially from the birth of virtual reality, which are starting to try to give an haptic feedback to the movement of the hand. The different approaches are mainly related with how much force you can impress on the hand and where do you want to give that kind of force. So, for example, this design is giving force to the whole fingers, while this one is using vibrators actuators to only give sensation of a tactile sensation on the fingertips. And finally, on usability design, we have several indexes that we can measure that comes from human computer interaction state of the art. So we can measure the learnability, the memorability, and the comprehension that comes from human factors. So basically, we want to see if using an augmented reality interface is easy to learn for non-trained individuals, if it is easy to remember how to use an augmented reality interface, and if using an augmented reality interface can give you a better comprehension of what you are doing compared to traditional methods. And the other three are based on usability goals, so we want to see if it is efficient to use those kind of interfaces, if we can cope with the errors, with the interaction errors in an efficient way, and if the users are satisfied with the system. Those kind of indexes can be measured by means of experiments or questionnaires, usually. But depending on the index, we have to devise the task tracing characteristics that we devise in the experiment in order to isolate the correct index. So, for example, the low-level tasks, for example, task completion times or number of completed tasks, are measures which can use to isolate micro-level task characteristics, so motor-level characteristics or perceptual characteristics. If we want to see higher-level cognitive aspects of augmented reality use, then we have to have more complex tasks and devise complex experiments which, for example, are repeated over time to see, for example, if the memorability of the interface is good enough. So now I will show you some of the preliminary results that we have obtained during the first year of my PhD. I analyzed the perceptual differences between two different types of head-mounted displays, and then started to work towards the construction of an haptic glow, and I started to work towards the detection and the tracking of the pose estimation of the hand. Okay, so about the comparison of two different types of head-mounted displays. We know that in virtual reality, the depth perceived is compressed, and there is several documentation about that fact. By extension, since the type of head-mounted displays is similar to virtual reality devices, we can expect that similar compression will be experienced also in those devices. There are several depth cues which are behind our comprehension of the depth. So it is not easy to isolate the single cues in experiments. So it is still not yet fully understood which cues are causing that depth compression, or if there is a combination of the cues which is the main culprit behind that underestimation. The two different displays that we use are the MetaVision, which is this one, is an optical see-through device, and the Google Cardboard. So it's a smartphone which is attached to a pair of lenses, and it transforms the smartphone in a cheap virtual see-through device. It is appearing in ISMAR conference soon. The experiment was devised in this way. So the user was standing still with no linear help, so they could not see any linear perspective to understand the depth. There was a Kinect recording the movements of their hands, and then some cubes, some target objects were appearing in a random volume in fixed position here at fixed intervals. So the users had to perform a precision homing task, so they had to try to reach for the cubes in the place that they thought the cubes were actually appearing. And while they were doing that task, we were registering the position of the hand and the real position of where we were placing the cubes. we devised two different tests. In the first test, the user could not see the internal augmentation of the hand, so they had no internal feedback. In the second test, the subjects could see an internal feedback of where their hand were placed inside the unit device. We proposed the experiments to several volunteers, and sadly we had to discard part of the data because of the noise in the data. Here we can see the difference between not having the feedback and having the feedback. Here you can see this 3D printed handle was used to register the position of the hand because Google Cardboard is not tracking the hand. So this is a primordial way to register the position of the hand with the Google Cardboard. Here also you can see the problem related with not being able to track the hands, so that the occlusions, this part of the glow should have been actually not rendered because it should be behind the arm, and here it is rendered because the system doesn't have an inner registration of the table and everything else. It is only tracking this image. This is the distribution of the data that we obtained. So the red dots are the span position of the targets, while the blue ellipses are the clusters of the hand position. Is the principal component analysis of the cluster of the positions of the end of all the users. So, for example, when a cube appeared here, the distribution of this of the user was of this ellipse, and so on for the others. There are 4 graphs because the first 2 are of the first experiment and without the internal feedback, and the second 2 are with the internal feedback. The first image is from the user who used the visual citrus, the Google Cardboard, and the second image is for the users who used the MetaVision. As you can see here, the variance of the clusters of the hits is very high. So here the perceived distances are not really well. There is a misperception of the position of the target. So, for example, sometimes when the target was appearing here, some users place the hand here as comparison. When the internal feedback was provided again, the results improved a little bit for the visual C2, while remain pretty much constant for the optical C2 device. Little words spent on the optical C2 device. We can see that both graphs are the variance on both graphs is limited. So the result obtained with the perception obtained with the optical C2 device is considerably better than the video see-through device in this experiment setup. This is the table of the mean error perceived. We can see that in the first test, in the first experiment, the error of the depth for the visual see-through device is very high. Internally, it has been registered to be around 20 centimeters. And moreover, the Kinect data is also showing even more underestimation. So as you can see that the two data are misaligned, so it means that the internal registration of the data is also not perfectly overlapped with the real measures, because the Kinect was actually measuring even less. Well, for the optical see-through device, the internal measures and the Kinect measures are more or less the same. So the internal registration of the MetaVision is better in that regard. So it is able to overlap the virtual world with more fidelity with respect to the real world. And here, in this table, we can see the depth compression, the horizontal and depth compression rates. So if that number equals 1, it means that there has been no compression. If the value is under 1, it is a measure of how much the depth was compressed. And if it was over 1, but there are no cases, it would have meant that the user were actually overshooting the target's position. So from here we can see that when in the first experiment, so when there was no feedback, the depth perceived was very compressed. There was a high factor of compression, while for the metavision in both axes there is still a small compression, but not so evident. In the second experiment, we can see that the compression of the depth is lower than in the previous case, but it's still worse compared to the optical see-through device. This is some of. This is not the glove which I am devising, but the design is similar to the final setup that I plan to use. So I started to build an haptic glove by using a WP development board, which is programmed with Python. The design should include the 5 actuators for the fingertips, and it should be working under Bluetooth communication. The vibrator basically should give a small tactical inputs to each fingertips when the user is touching virtual objects. So the glove must communicate with Unity. The Unity must first register the position of the hand. When it sees that the hand is inside a virtual object, it must send the input to the actuators to vibrate to indicate that the user is touching something. And finally, the last part of my first year here, I started to work on an hand pose estimator. I wanted to use OpenPose backbone, but I had to build a custom hand detector because OpenPose, like you see here, is able to perform the hand pose estimation very precisely, but it localized the hand on the basis of where the rest of the body is detected. So since in augmented reality we are not detecting the rest of the body because the point of view of the camera is egocentric, so it's like it was overlapped with our eyes. We have to provide to the system the location of the hand in the image before it is able to perform the pose estimation. To obtain the hand detector, I trained the SSD Coco model. By transfer learning, I used the Hego Hands dataset, which is a dataset of hand pictures obtained with Google Glasses, so with augmented reality and mounted display, which is already labeled and so on. But preliminary results were obtaining too low frame rates for this system in this configuration to be usable for augmented reality. So here, the future work that I plan to do in the following 2 years. As first thing, I plan to investigate the learning aspects behind the usage of augmented reality. Then I want to repeat the experiments of the comparison of the 2 head-mounted displays. I want to finish the design of the haptic glove to improve also the hand detection, so finish the work on the hand pose estimation, see if I can obtain good enough hand pose estimator, or if I have to go on a gesture detection. And then finally, to integrate some kind of environmental registration, so the performance is to see what kind of SLAM we can integrate in augmented reality system, and then perform a final validation of all the system together. Investigating the learning aspects. The goal of this project would be to understand if by using augmented reality interfaces we can, for example, obtain higher compression rates compared with traditional methods. So for example, if there are instructions to mount a machine, if giving those instructions as animations, 3D animations, where we can manipulate the single objects and see how they merge together, it can be better than just studying the schematics, if it can be easier to understand to non-trained individuals. If the system is easy to use, and so on. Since we have, as I said earlier, different usability index that we can measure, we have to define which index we want to measure, and then define the tasks accordingly to be sure that we are actually measuring the right indexes with in the right way, following the state of the art. This is the experiment that I have already done, but should be performed again in a more controlled manner, because in this situation we compared a system which was monocular, so the Google Cardboard, with a MetaVision, which is a much more expensive system, and it was not a really fair comparison. So the plan is to repeat this experiment, but with a stereo vision video see-through system, to obtain a more representative result of the comparison between those entire type of devices and those entire type of devices versus just obtaining the differences between those two specific devices that I used the first time. Also, the devices should be synchronized and calibrated. So, for example, if we end up using the smartphone, it should be synchronized with the connector so that we can synchronize the data and we can compare the data in a more precise manner. And the final goal of those experiments would be to see if we can achieve an effective interaction with both type of displays, or with both type of head-mounted displays. If we see that we cannot achieve with current implementation an effective interaction with, for example, the video see-through devices, it is possible to implement, for example, rendering techniques to show the objects closer to the user if we see that the depth perception is compressed no matter what. So we can change the way that the objects are displayed. The haptic glove that needs to be finished needs to be working under several restrictions, because we want the glove to not restrict the user movements. We have to see if we want to integrate some fiducial markers on top of the glove to make the tracking of the hand easier. So if you want to simply put markers or sensors, or maybe inertial sensors, we have to see if the design can be expanded. The glove must be, it's an experimental glove, so we must take in consideration that we want to use it to make experiments with a lot of test subjects, so it must be robust enough that we can make it usable by different people without wearing out very quickly, and it must be cleanable easily. So we have to see if, for example, we want to allow the user to use a hinder glove, disposable hinder glove, so that we can avoid cleaning the real hand, or we can find an easy way to detach the circuitry from the the glove on which it is attached, to clean the cloth glove. And the final glove must be integrated in Unity, like I said, with C# to handle the communication between the inner registration of the hand and the actuators, to handle the inputs. Here is the hand detection part, the hand interaction. So I plan to explore more in detail if I can obtain a hand pose estimator which can work with augmented reality systems. So we have to evaluate the kind of performance that we can obtain while devising full pose estimation. If 26 degrees of freedom are too many, it is possible to try to see if we can use a simplified kinematic model and see if it is possible to achieve good enough performances. And if we see that the performance is still too low to be used for augmented reality system, then we will back up on a gesture detector. For the environmental registration part, there are several aspects that which needs to be defined. So we have to see which hardware we plan to use. So if we want to perform some SLAM using the depth sensor, or monocular camera, or depth camera, and so on. Because of course, if you are able to perform it with monocular black and white camera, It works with everything, but if it is too slow with monocular camera, then maybe with stereo camera you obtain better results, which can be used with at least some devices. The goal of this implementation is to be able to have an external registration of the world, so that if you have a virtual object and you launch it on a table, it can detect the collision and bounce on the table, versus you only have some fiducial markers around and you can only interact with a specific set of objects. Finally, as last project, in the last part of the 2 years, I plan to build a final application which integrates all the modules developed earlier to see if with internal registration and detection and haptic feedback and so on, then the internal the user is able to achieve an effective interaction, which is hopefully better than current interfaces, so current Windows interfaces, and so on. And I think yes, this is the expected work plan. So I have split evenly all those tasks in 3 months intervals, and left some time at the end for the thesis. I think it's finished. Yes, it's the references of the hand detector studies which I've discussed. There are questions? Yes?
So the globe can be used in isolation, so without Unity?
No, the glove cannot be used without Unity because you have to the processor has to send the inputs to the actuators, but you have to know when to send the.
Yeah, but you can communicate with the processor. What are the SDK or?
No, we have to build this from scratch. So there is no. Yes, you can send technically.
So this is something that you have to.
Okay, no, I understand what you say. Yes. Yes. But I mean, okay, you can integrate the glove with other systems. Yes, you can do that.
So the glove is not.
Because this is not the one that we are. It's the concept is similar, but it's not the one that we are.
So you're building one from
yes,
scratch.
Yes.
Okay.
So once the processor, once the glove is built, it is possible to modify the processor to integrate with another, for example, graphical engine. But you have you need to give the inputs to the processor to.
Principle
yeah.
Yes,
you just have to program in Python the processor.
Okay, there is in Python.
The processor is programmed in Python, but you have to integrate it in Unity and C#.
And why Python? The processor, why is a Python processor? Not another.
Because the type of processor that we choose are the Wi-Fi and Bluetooth integrated in the car.
Yeah.
So and they made it in such. I think it's Python, or there are choices. I think it's also programmable in C++, but I'm not sure. It's called WIPI, I guess for a reason.
No, I was wondering. And it has this. So for the sensors for the touch sensors.
The
specific device for the.
I mean, those actuators are not taptic, are just vibrating basically.
Okay.
Yeah. So it just gives some kind of.
So, but the processor is specific to the devices, or?
No, it just have input-output devices, and you just say, okay, turn these actuators on, and yes, it is possible eventually to modify the type of input.
So you could use a lead, for instance.
Yeah. Yes.
Okay.
It's just design choice. It is possible to modify the perceptual input that the vibrators are giving, because you can modulate the intensity of the vibration, and depending on the vibrators that we end up using, then you can choose the waveforms. So you can give this kind of like if you put waves going in a certain direction, you can simulate different tactical sensations. But we have to see what first I'd say that the plan is to first build the first version working with all integrated with Unity and so on, and then see if we can improve it by extending the gamma of sensations that we can provide and so on. Yes?
So, okay, concerning the interaction with the environment,
Mm-hmm.
so, okay, if I understood well, you are
Yes.
interested in the augmented reality application, but in principle, you could have also, I mean, sensors in the real world.
Yes.
You were talking about that at some point.
You mean in the about the fiducial markers?
Yeah.
The point of fiducial markers is that it's like this one. If you can avoid using fiducial marker, it's better because you can use your display walking around in the street.
So fiducial markers are meant to, I mean,
yes, you need a fixed marker somewhere which is used as a reference point.
Yeah,
so if you don't look at the marker, you cannot see anything.
But does it make sense to have to interact with other devices? Not fiducial markers, but other devices in this setting.
And it is suggested by manufacturers of the headsets that if there are multiple augmented reality devices connected in the area, the augmentation should be the same for everyone. So if 3 people use a MetaVision, they should be interacting on the same hologram. But that's still not really, the cooperation between different mounted displays is not really explored at the moment because the problem is still in the environmentalization. So if it is still hard to place virtual object and making it stand still synchronized with other people.
I was not talking about other people, but other devices.
Yeah,
it should be possible. Not the same type. I guess.
Technically, it should be possible to have it on different devices on the same. If you have fiducial markers, it is easy to implement. If you are not using virtual devices, it is trickier because you have to estimate the pose of everyone, make an augmentation which is coherent for everyone else. Yeah, so it's a little bit trickier. Yeah. You have a question? Get it?